Okay, thanks very much for the introduction, and thank you all for coming along. I'm pleased to see that you, like me, believe that a bit of quantum mechanics is the best way to start any weekend, first thing up. But as it's the first talk, and quantum is a heady brew, I'm going to start off a little bit slowly and of course, rapidly speed up in a time-honored way. So let's begin here. Coffee's much on my mind at the moment, as I can see it's on your mind. This is one of my favorite, probably my favorite cafe in Vienna. It's the Café Central. It's not quite as smoky as that anymore. That was a few years ago before the smoking ban, so I encourage you to go there. It's a fun place. Now, of course, I have to make some tenuous segue to quantum mechanics, but before I do that, I'll just mention this book, which I really enjoyed. This is a fabulous book, which goes on and on about the wonders of coffee and perhaps its connection to physics, to fuel ideas, at least theoretical physics. Anyway, some of you may have read this book. It's great fun, about Gödel and Turing and machines and quantum, and not so much quantum mechanics, but computing. So my tenuous segue is to Erwin Schrödinger, who, of course, was educated in Vienna in the late 19th century. And of course, he, as everybody knows, is pretty central to the business of quantum mechanics. Unfortunately, he has a bit of a bad rap in the popular press. He's more, somehow or other, become associated with a man who does not like cats. But a large part of his scientific work was strongly influenced by the fact that he was, in fact, educated in Vienna in the very famous school of people like Boltzmann and Mach. And this is a quote from one of his essays about his life, where he says he was born and educated in Vienna with Ernst Mach's teaching and personality still pervading the atmosphere. Both Boltzmann and Mach were just as much interested in philosophy as physics, and in a letter to Eddington much later, he says, Boltzmann's approach consisted in forming pictures, mainly in order to be extremely certain of avoiding contradictory assumptions. So this emphasis on pictures and the ability to imagine the quantum world, I think, is extremely important in Schrödinger's work, and in fact is perhaps for him something of a contrast to a similar formulation, to a completely equivalent formulation of quantum mechanics given by Heisenberg about the same time, which is, well, certainly not easily picturable because it's based on matrix mechanics. But Schrödinger's, as everybody knows, is based on a wave function, something which we imagine we can picture, something which oscillates like waves in the ordinary course of physics. But of course, that can be a little bit misleading, as we'll see. The waves that Schrödinger is referring to are actually waves of probability amplitude. Unlike the electromagnetic field, which is a wave, where you can go out and measure the electric field or the magnetic field, nobody can measure a probability. It bears the same relationship to stuff as number does to stuff. If you assign a probability, you don't measure it. When you toss a coin, you say the probability of a head is half if it's a fair coin, but when you actually look at the coin, you see a head. You don't see a half. You don't see a probability. So a probability is an abstract concept, and the probability amplitude, the wave function, inherits that same abstraction. So while Schrödinger's beautiful picture of quantum mechanics being based on interfering waves is an extremely powerful pump to our intuition, it can sometimes be a little bit misleading. Okay. So I want to say a little bit about why I'm so excited about the current era in quantum physics. I head up an Australian Centre for Engineered Quantum Systems, where our objective is to actually engineer artificial quantum systems of considerable complexity involving moving parts, electronics, light, information processing, all as integral parts of the complex function of the device. And the objective is to push our controls right down into the hidden layer of the physical world, the level of Schrödinger's wave function, which we might now refer to as the level of quantum coherence. So we've moved beyond the stage of just taking stuff, quantum stuff, and studying it, to actually engineering quantum stuff and ordering it to our purpose. And we can do that because of this hidden layer of the quantum world. So controlling quantum coherence will enable us to reversibly change irreducible uncertainty into perfect certainty. Now, what do I mean by irreducible uncertainty? Well, I'm going to try and capture quantum mechanics through two principles which I've arbitrarily attributed, one to Bohr and the other to Heisenberg. The first central lesson of quantum physics is that the physical universe is irreducibly random, that at its deepest level, there are events for which there is no explanation. In a sense, I'll explain in a minute. There is an irreducible uncertainty. It's not just a case of, well, I just try a bit harder and study it a bit more carefully and I'll be able to get rid of all that uncertainty and know really what's going on. There is a fundamental level of irreducible uncertainty. And it's expressed by this, that given complete knowledge of the state of a physical system, there's always at least one measurement you can make for which the results are completely random. This is the first clear statement of quantum mechanics. Now, you might think, well, in a universe like that, how is anything possible at all? How is it possible to build anything? It certainly doesn't look like that. It's not a complete, roulette game when you walk out the door. And the reason for that is the flip side of the coin. And I've attributed that to Heisenberg, which says that given complete knowledge of a physical state, there's always at least one measurement, the results of which are completely certain. Same state, depending on how you look at it, appears to be a source of irreducible uncertainty, a kind of unfathomable well of randomness, but it's also possible to have complete certainty in that same state depending on how you measure it. And the fact that these two things can cohere in one and the same description of reality is at the core of quantum mechanics. How do we see that? Well, I'll just quickly summarize some of the ideas and then give you some illustrations of how it works. The key idea is how probabilities enter into quantum mechanics. They're not primary. Quantum mechanics kind of falls into two bits. There's a bit which tells you how to calculate probabilities in the first place, or probability amplitude. There's another bit that tells you what to do with them once you've got them. So it's really a calculus for determining the probabilities of measurement outcomes, but the probabilities themselves are not primary. Probability amplitudes are primary, and we square that probability to get, we square the amplitude to get the actual probability. But here's the extraordinary feature which is connected to these two principles I put up before, and that once you have the probability amplitudes for one kind of measurement, maybe the completely random one, you know the probability amplitudes for every other kind of measurement. And this is why we call a list of probability amplitudes the state. So a state in the quantum theory is a list. It might only have two elements in the case of a qubit, or it might have infinitely many elements in the case of a position of a particle, but it is a list of probability amplitudes for the results of one kind of measurement. And then you can get a list for the probability amplitudes for every other measurement by essentially just cranking the handle of the quantum machinery and churning it out. Now, that's an extraordinary feature. It's not the case in ordinary classical statistics that this holds, but it is a deep feature of quantum mechanics which lies at the heart of the Heisenberg uncertainty principle. Okay, so let me just give an illustration of these rather abstract thoughts. So let's take a very simple experiment, one that we're familiar with in quantum optics. We imagine we have a laser, and we direct it towards a semi-silvered mirror, or a dielectric interface, which classically would reflect 50% of the light and transmit 50% of the light. Classically, we would think of that as a wave coming in and being just split evenly. Half the amplitude is reflected, half the amplitude is transmitted. But we know that if we turn the intensity right down, we eventually begin to see the graininess of light, which Einstein pointed out in his explanation of the photoelectric effect. So let's imagine in this experiment we turn the intensity of that laser right down, so that most of the time we detect nothing. So we have these two little counters that go click whenever a photon hits them, and we have the intensity so low that most of the time we see nothing. Every now and then we see a click, but one thing you never see is two clicks simultaneously, because the photon does not split at the beam splitter. It either is reflected or it is transmitted. What any given photon does is completely random. So we see here the simplest manifestation of the irreducible randomness of quantum mechanics. Even if I tell you everything there is to know about that laser and the light and the beam splitter and the optics and the photon counters, pin it all down. In any given run of this experiment, you will not be able to predict whether a given photon is transmitted or reflected. In the long run, of course, it's roughly 50-50 if it's a semi-silvered mirror or some sort of beam splitter. So you can see I've labeled the photons coming down from the top with a 1, and I could also have photons coming up from the bottom, which I've labeled as 0, in anticipation of assigning bits of information to these quantum states. So this looks like a coin toss, right? This looks, if it's irreducible uncertainty, well, this looks pretty much like a coin toss. But let's just do it again. Let's just toss the photon again. Let's just force it after it's been reflected or transmitted to do it again, to make another choice, either on the same beam splitter or perhaps a different one. So let's just put two mirrors where the detectors used to be and force the photon to make another choice. So if it's reflected at the first beam splitter, it now is directed towards another identical beam splitter, and it can be reflected or transmitted. Again, I stress, most of the time you see nothing. Every now and then you see a click, and you only ever see a click at one detector or the other. So is this like tossing a coin twice? Well, if it were, then the detection probability should still be 50-50. There are two ways to get to the upper detector. It can be reflected at the first beam splitter and reflected at the second, or it can be transmitted at the first beam splitter and transmitted at the second, both of which are equally likely. Both have a probability of a half times a half. So we add them together, a quarter plus a quarter gives a half, and so we're back to a coin toss. But of course, as you probably anticipate, when we do this experiment, that's not what we see at all. We can set it up in such a way that detection at the upper detector is certain. That is, we've gone from irreducible uncertainty at the first beam splitter to complete certainty by forcing the photon to make the attempt twice, without changing anything about the quantum state of the light in the source or in between. So we see here that depending on how you interrogate the light, the quantum state of the light, we can either have irreducible uncertainty, complete randomness, or complete certainty. And that's the trick of quantum mechanics. So in an engineered quantum system, we push the levers down and we start moving them and controlling them to move the amplitudes around in such a way that we can render what was formerly completely uncertain, completely certain, to achieve some particular practical end. And I'll talk about some of those later in the talk. So you can get a hint of why that must be the case. It's intimately connected to time reversal invariance, because this is exactly the same experiment with slightly different topology. Instead of putting it on a different beam splitter, I put mirrors and just reflect it back. And if it's all completely time reversal invariant, as quantum mechanics says the world should be, it should just go straight back to the D detector. So that gives you a hint of why this one is always detected at the upper detector. So there you go. We have perfect certainty out of irreducible randomness. Now, I'll give you a quick sketch of how the formalism takes care of this. It basically comes down to a generalization of Bayes' rule, which I'll call Feynman's rule, which says if an event can happen in two or more indistinguishable ways, just find the probability amplitudes for each way it can happen, add them up, and square it. And that's enough to explain what's going on here. So here's a quick sketch of it. A count at the upper detector, as I said, can happen in two ways, two reflections or two transmissions. So we need the probability amplitudes for each of those ways it can happen. Likewise for a count at D, which requires reflection and transmission reflection. We need those probability amplitudes. But once we've got them, we just add them up and square them to get the corresponding probabilities for detection. Now here's the trick. Where do those probability amplitudes come from? This is the quantum probability calculus part. To actually get the probabilities in the first place is not so simple. You have to do a bit of quantum optics, a bit of physics, and sort of a few calculations. But you quickly discover that they're given by the following numbers. That is, we just assign a quantum state before the beam splitter is 1, 0, which means it's certainly going down. But after the beam splitter, it's not certainly going down. It could be reflected or transmitted. And the quantum state is a list of these probability amplitudes. Here it's a list of 2 elements. So if it's coming down, it's transformed by the beam splitter into this case. So if we put a detector there and a detector there, we square these amplitudes, we get a half. So we're back to the 50-50 beam splitter. Now here's the key element where time reversal invariance enters. These two states, going down and going up, are completely distinguishable classically. These are mutually exclusive possibilities. And the quantum theory must account for that and must not allow that to ever change. So after the beam splitter, we have to have two different states that we assign. So we can't just simply assign 1 on root 2, 1 on root 2 for that, and the same for this, because then we'd have two distinguishable states going to two indistinguishable states, which is not allowed. The way quantum mechanics fixes it is puts a minus sign in front of one of these, which guarantees that this will be consistent with Maxwell's theory and consistent with time reversal invariance, and that changes everything. So now we run that simple calculus of Feynman's rule. we calculate the probability amplitude for 2 reflections, 1 on root 2 times 1 on root 2, get a half, 2 transmissions, a half, reflection transmission, a half, but this one's different, transmission reflection, because in this case, one of the photons is reflected from the other direction on the beam splitter. Now we put it into the formula, and you can quickly see that that case is 1, and the other case is 0, because these two probabilities cancel completely. And that's the essence of how we get this complete certainty from an irreducible uncertainty in the quantum calculus. I stress, underwriting this is a deep fact of the reverse time reversal invariance of the universe. Okay, so let's move on to apply that to something else. So I want to spend a few minutes now talking about quantum measurement. So here's the world's largest quantum machine. It's the Laser Interferometric Gravitational Observatory. It's just two, basically, what I just told you about is basically that, a photon force to make choices between paths in an interferometer, but they're very big paths. They cover a kilometer or so. What is this? Well, it's designed to detect gravitational wave, which are tidal, if you like, distortions in space and time due to massive accelerations of mass somewhere in the universe, hopefully not too close. They pass through the device. If they pass orthogonal to the arms, so the arm is basically a laser with a semi-silvered mirror, it can go into here and bounce around a while and come back, and then either can be transmitted or reflected. And this one does the same thing, so it's pretty much the sort of thing I was just describing. When the gravitational wave passes this way, it shrinks and stretches the arms in a kind of contrary motion. It's a kind of quadrupole oscillation of the lengths of these arms. So clearly, if you can monitor the lengths of the arms or the relative change in the length of the arms by these probability amplitudes, then we can get an idea of the strength of the gravitational wave. Amazingly enough, you can get a sensitivity of 1 part in 10 to the 18. So over 1 meter, you can get a sensitivity of 10 to the minus 18 meters, which is what you need to do if you're ever going to see the effect of any kind of typical gravitational wave here on Earth from astrophysical sources, unless something truly catastrophic happens, which we hope it doesn't. So here's the idea. The gravitational wave comes in, it just moves this mirror around a little bit, and that changes the probability amplitudes for these two paths. And so as it moves, it changes the probability amplitudes, which is going to change the conditions for the probabilities at the output. And from the probabilities at the output, we back out the probabilities for, we back out the size of the gravitational wave. So here's how it works, exactly the same as before, but now I need to tell you how to change the probability amplitude if I move this mirror a little bit and make these paths non-equivalent. Well, it turns out I need some complex numbers now, so in between the 1 on root 2 and 1 on root 2 for these beam splitters, I insert this little complex number, which has modulus 1, so it's not changing the probabilities in any way, but it is changing the amplitudes. So I just run through the same calculation as before, and now I see that instead of getting 1, I get cos squared theta, which is determined by this little displacement of the mirror. So the trick is now we can turn this into a measurement by sampling that probability distribution. So we send a single photon through. In each trial, of course, you either get a click at one detector or the other. That's all you get. You don't see any smooth cos squared thing. You just get a click. You get a binary number, 1 or 0. So we need to run it over and over again. And this is typical of all statistical theories. You need to sample the distribution. So we run it n times, varying theta, perhaps as the gravitational wave is passing through. And you start to build up some distributions like this. They're not smooth, but if you make more and more and more samples going out to 100, you begin to see the cos squared theta pattern emerging. But any finite number of trials, you have to try and back out what the theta is. What, is this theta pi on 2 or a little bit bigger than pi on 2? You have to make a guess on that. So you have to estimate what that should be. So you might say, well, the average value of this result, which is either 1 or 0, upper detector or lower detector, turns out to be cos theta. The uncertainty is given by sine squared 2 theta. And in many, many trials, you can convince yourself that the uncertainty in backing out what theta is goes down as 1 over n. The more trials you make, well, this is the variance. The uncertainty goes down as the square root of that, so it goes down as the square root of the number of trials. So you need to make lots and lots of trials to actually do this. And you can do that perfectly well. Just make n bigger and bigger and bigger. So this sounds great. We'll just keep running this thing with as many photons as possible. Let's not use 1, let's use 10 to the 20, and then we'll be in great shape. We should be able to measure arbitrarily small displacements in this mirror. Well, you quickly discover that you forgot one key principle, and that's the Heisenberg uncertainty principle. and that if you try to do that by measuring the mirrors ever more accurately, somewhere or other you're going to pay the price. The irreducible uncertainty of quantum mechanics will enter again, and this time it enters through the fact that photons can be reflected or transmitted at random, as we said, at each of those mirrors. But if one of them can move, which it must be able to move to respond to the gravity wave, then if a photon is reflected, it gives a little momentum kick to the mirror. And because of the irreducible uncertainty, it can be reflected or transmitted at random, so it's giving random kicks to this mirror. So it begins to shake. We're all familiar with this. We know that this is going to lead to noise. If you are in your cottage with a tin roof and it starts to rain, the first couple of drops you hear is clicks. But as more and more rain comes down, you just hear white noise, this sort of shh sound in the background. Same thing happens for the gravitational wave detector. The mirror is just shaking, and if it's shaking, it may be shaking too much to see the small displacement due to the gravitational wave. And sure enough, that's what happens. You find if you're just trying to crank up the photon rate to improve the sensitivity, eventually this radiation pressure noise kicks in and enforces the Heisenberg uncertainty principle. So it's always the case in any measurement. The Heisenberg uncertainty principle is a very abstract general way of referring to it, but in any particular measurement you can point to the physical causes of what enforces the Heisenberg uncertainty principle. This was recently measured just this year by Cindy Riegel and her co-workers down in Boulder, and here you see the rising degradation in the accuracy of the measurement as you crank up the power in the laser, so you're beginning to see the radiation pressure noise. This is a beautiful experiment that looks pretty much like this little toy model here. They have a mirror that can move. Okay. Now let me talk about the next important key aspect of quantum physics, which is again a manifestation of the way the calculus works, and that's quantum entanglement. Quantum entanglement refers to correlations between two or more measurements. We've just been talking about the statistics of single measurements. Now let's look at the statistics of joint measurements. For example, we might say, if we're using 10 photons, what's the probability that two detectors click together? That's a correlation measurement. Well, it turns out, and I'll say a little bit more about this, is that measurements made on the joint state of separate systems, if it's a quantum state, can reveal correlations that cannot arise in any classical statistical theory. By classical statistical theory, I mean one based on classical mechanics, in which we think that if there's any uncertainty about where a particle is and how fast it's going, that's our problem. That is, we don't have enough information. If we had enough information, we would know where it is and how fast it's going. That kind of classical ignorance interpretation of states leads to correlations that have to satisfy particular constraints, and those constraints are violated in quantum mechanics, as I'll explain in a minute. So quantum correlation is often called entanglement. It's really applying Feynman's rule to joint measurements. So if I tell you that two photons have the same polarization, I haven't said whether they're both horizontal or both vertical, so there are two ways that correlation can be realized, and if that's all I know, and that's everything I know about the quantum state, that state of those two photons is entangled. But to draw that in the starkest terms, I'm just going to make a kind of whimsical analogy here to talk about classical correlations for a minute. So let's imagine you live in this little town called Bellsville, and the citizens of Bellsville got fed up with filling out survey forms every time they bought a bottle of Coke or did anything. And so they passed a constitutional amendment or a change to the state rules, which said that no more than the result of a single yes-no question can be recorded for any citizen. So you have one bit recorded somewhere by the government, and that's it, no more. That's all they know about you. And this is, okay, the government doesn't care. They probably lose most of the bits they get about you anyway. But, some major corporation is trying to sell you soda or something, might not be so happy with that. But the major corporations figured out a loophole. They've decided that for some bizarre reason in Bellsville, there's lots of identical twins. So they realize they can ask a different question of each twin, get 2 bits of information, and those 2 bits apply to each twin the same. So now they've got 2 bits for each of the pair of the twin. So here's the questions I ask: height, sex, and eye color. And we need to make this very stark, so we'll just say the answer is either short or tall, male or female, and blue or otherwise. So if the twins are identical twins in this sort of imaginary world, if you get plus for one twin, you always get plus for the other. If you get minus for one twin, you always get minus for the other, no matter what question you ask. So they're perfectly correlated in that sense. So in every case where you ask the same question, you get the same answer. But what's really interesting is what happens if you ask different questions of each twin. There's no point in asking the same question of each twin. we're not getting any more information than we would have got if we just asked one. But if we ask a different question of each twin, we're getting a little bit more information. So the really interesting case is what are the correlations when you ask a different question of each twin? So the simplest way to calculate this is to imagine that the results of the survey, these trays, if you like, are determined by some sort of hidden genome, which determines whether or not you have plus, plus, minus. So SHC would be plus for S, plus for H, minus for C, because that twin carried that gene. The other twin carries the same gene because they're identical twins. So you know straight away. Now notice there are 3 possible outcomes here, but there are only 2 twins, so you can only ask 2 questions. You ask one question of that twin and one question on that twin. So one result is always unknown. So we can quickly calculate the probability that if I ask S, I get plus. If I ask H, I get plus. And the other one's unknown. I just make sure I have plus plus for those 2, but I don't know the other one, so I use Bayes' rule and just add up the 2 probabilities to get plus plus, given that I don't know how it's realized in the other tray. And if all these genomes are equally distributed, there must be 8 of them, then the probability is 1/8 plus 1/8, which is a quarter. So if I conclude that to get plus plus for different questions on each twin is a quarter. But let's vary it a bit. Let's just say, what's the probability to get the same answer for different questions on each twin? Well, it doesn't take too much to work out that that's going to be a half. So now I go out and sample this data, get a huge table, I start searching through it, and I discover that whenever I ask a different question of each twin, half the time I get the same answer. Might be plus, or might be plus plus, or it might be minus minus. That's completely random. So now let's try the same thing with quantum twins, which is stretching it a bit, but anyway, let's push on. It turns out that there are certain kinds of nonlinear crystals which will down-convert light. They'll take a photon and destroy it, and simultaneously create 2 pairs of photons at lower energy. Take the simple case where the energy of each is a half the original energy. That's called down conversion. Now, beam splitters don't do that because they're not like this. They don't split photons. If they did, they would change the color. So this thing changes the color of the photon. So we send in one, say, green photon, and we get 2 red photons out. Now, it's possible to arrange things so that this can lead to highly correlated polarization. So if we arrange these sources correctly, it turns out they will always produce identical photons at the same time, at random times, but at the same time they're created. And they'll always have the same polarization. They'll always be both horizontal, both vertical, both circular, left circular, both right circular. But that's all we can say. They have the same polarization. So we put some little polarizers in to ask the right question, and then we check. Is it horizontal? Is it vertical? Is it horizontal? Is it vertical? And we make 3 choices for this angle, which is like asking 3 questions of each twin. The data is still binary, 1 or 0, up at the horizontal detector or down at the bottom. And now you run the experiment and you discover something quite shocking. That is, for certain settings, the probability that both different questions, different settings give the same answer is a quarter, not 1/8. Every time you do an experiment on each photon separately, you discover when that one's horizontal, when that one's vertical, and of course whether it's horizontal or vertical is completely random, just like in the case of twins. But when you force them to answer different questions together, the fraction is reduced. Again, there's a simple explanation based on Feynman's rule. Turns out we need to know the probability amplitudes for all these triples. We need to know the quantum state of this joint photon. I can't tell you how to get that. Again, that requires a bit of extra quantum mechanics. But once you've got it, the calculation's really simple. The probability, you just find the probability amplitudes, and we see a minus sign appearing again. It turns out we now just have to add these together, and this time there's some cancellation, and so we get an 1/8. So plus plus is an 1/8, minus minus is an 1/8. Add them up, you get a quarter, and of course the different case is 3/4. And that minus sign makes sure that this is below 1/2, and it's a quarter. So again, we see this strange way in which probability amplitudes determine unexpected results in quantum experiments. So let's return to this idea that we can make binary digits out of photons going up and down towards a beam splitter. So we've just seen that we can't really think of the photon on this side as a coin toss. It's not really going up here, but we don't know that, if it was reflected or transmitted. So we refer to this as this funny situation. We're not used to this in the real world. So many years ago, Ben Schumacher invented this great word qubit to refer to the kind of bit that it is after it's been forced to make this choice, but we don't know yet what's been realized. So that's a qubit. We can use that to code bits of information. So we're going to say that when a photon is going down, so the probability amplitude is a list in this simple experiment. There are only two possibilities: it's going down or up. If it's going up, it's detected here. If it's going down, it's detected here. So every state is a list of two probability amplitudes. The initial one is always going down, so it's 1, 0. We'll say that encodes 1 bit of information. This one, if a photon's going this way, it's definitely going up, so its state is 0, 1, and that encodes 0, that particular symbol of information. After the beam splitter, we can't say one or the other, because the probability amplitudes get transformed in that strange way I indicated, with 1 on root 2, 1 on root 2, minus 1 on root 2, 1 on root 2. So we represent that as follows. We say that after the beam splitter, we had a single binary digit 1, which is now a superposition of the two possible states of that binary string. And there are two possible ways we can superpose it, because we need to make sure this state, this 1 state, is always distinguishable from the 0 state, even after the beam splitter. So 1 and 0 are the two mutually exclusive possibilities for a binary digit. And the quantum mechanics keeps care of that by putting a minus sign, as we saw in the list of probability amplitudes. So this is just a shorthand notation to keep track of how our binary strings are moving through this device. So the interesting thing is that if I have two beam splitters, I can now have 1, 1, 0, 0, 1, 0, and 0, 1. So I can encode 2 bits of information, or 4 possibilities. So the experiment on photon twins was like this. And now I see that 2 beam splitters can produce a superposition of the 4 possible ways in which I can order 2 binary digits. So 2 bits of stuff gives me a superposition of 4 binary digits in one go. So clearly one can continue that game, put 3 bits of stuff, 3 mirrors, and I can get 8. At the end of the day, if I have n mirrors, I can take n physical qubits and encode 2 to the n binary numbers simultaneously. Of course, which one I get will be random at the end of the day if I actually look at it. But let's not look at it. Let's just have all together and try and process all that information in one go. So that's the idea of a quantum computer. We try and find some way to represent the binary digits in a code so that they're, in a sense, simultaneously present to the machine. And we just keep putting mirrors and beam splitters and phase shifters and little moving things all over the place inside the box, and then arrange it in such a way so that we definitely get the answer we want, or at least we get the answer we want with high probability at the end. So essentially that's what a quantum computer is designed to do. And the reason it, in principle, should work much more efficiently than a classical computer is because of this 2 to the n expansion in the size of the way in which we can store and code information in quantum states. So this was realized long ago, first hinted at by Feynman, in fact, which is why I called one of my books the Feynman processor, but its clearest statement was given by David Deutsch in 1985, who realized that you could prepare the input as a superposition of all these inputs, run the computer once to give all values of the calculation, but if you look at it, you'll just get 1, of course, at random. So don't look at it. Let's run it again and see what we can do that might be useful. So you might ask yourself, when would you ever need to calculate a function on every value of its input but not care what the actual value was? Well, that's the case where all you're interested in is a property of the function. You might say, here's a function, is it constant? That is, every time I run it, I get the same answer, it's constant. Let's say, is it even? That is, half the time it gives 1, half the time it gives 0. So if you're wanting to evaluate a property of a function, on an ordinary computer, you just keep running it on inputs over and over and over again. That can take a long time until you finally figured out what the property is. But the idea is you can configure a quantum computer so that it just runs through with high probability. Another very important example is the period of a function. Let's suppose it's a function of the integers, 1, 2, 3, 4, 5, 6, 7, 8. And you want to know when does it start repeating. So f of 1 is 0, f of 2 is something, f of 3 is something. At what integer do you get to before it comes back to the same answer? So that's called finding the period of a function. And again, that should be much more efficient on a quantum computer. So what do I mean by efficiency? Well, it really is a question of how many steps I need to physically implement in order to get an answer. This goes back to the earliest days of computing and Turing, who suggested all computable functions are one that are computable by a universal Turing machine. These are recursive functions. Quantum computer can't do any more than that. So that's not the point. The point is it should be able to do it more efficiently. So how many steps are required? The example I gave of trying to find the period of a function that has an enormous period, say, an integer with 50 decimal places, if you keep trying to run it on every input before you finally find when it repeats, that's very, very, very inefficient. But the idea is a quantum computer could do it all at once. Why is that interesting? Well, it turns out one of the key features of finding the period of a function is involved in finding the prime factors of large integers of this kind. So one way to try and find the prime factors of a large integer is start dividing by 2. Well, it was a bit silly, but divide by 3 and so on until you eventually find one of the factors. And this is tedious. Obviously, you're going to need roughly the square root of the number of digits in here in order to factor it. If I add one more digit, I have to add root 10, basically, 3 times as many steps to get this to run. But Peter Shaw realized back in 93 that one of the key steps to finding the factors is, in fact, finding the period of a function on integers. And the way to get a periodic function on integers is just to make it a modular function, so like sort of clock arithmetic, so it goes around 12 times and then starts all over again. The trouble is this period can be very big. I won't have time to go into the details. The key is he realized a quantum computer, because of this trick of evaluating properties of functions, would run very efficiently, and this meant that you could actually factor large integers apparently more efficiently than you could with a classical algorithm. Of course, I'm not absolutely sure there isn't some clever classical algorithm that will do it as well, but we know for sure that in a quantum world we can do it efficiently. This is quite surprising. If the world was truly classical, that there was just classical hardware, Shaw's algorithm makes no sense at all. It just cannot run. But in a quantum world, this is the sort of algorithm that we can build a machine to do, and people have been trying to do that now for a while. I'll just quickly mention some of the best attempts. So there's a great deal of work being done on trapped ions. So the idea is you take an ion, which is a charged atom, and you try and trap it in free space. You can't do that with static fields because it'll always leak out in one direction or the other because of Laplace's equation. So you rotate the field. You add some sort of RF oscillatory component to it. So as soon as it tries to roll out along some unstable direction, you rotate the potential so it can't. And you trap the atoms in there. The binary digits are stored in the ground or excited states of some little transition in the atom, and you get them to talk to each other via their collective vibrational motion. So if one goes from the ground to the excited state, the atom recoils a little bit because they're all charged, they all start to vibrate together, and so they all feel whether one of them has been its quantum state has changed. And using that, you can come up with a way of doing quantum computing, as was originally pointed out by Peter Zoller and Ignacio Serra. So there's been a lot of progress on those. John Martinez later today will be talking about the huge progress on superconducting circuits, which back in the early 90s, of course, we weren't clear that this would have so much promise. This has been one of the great exciting features of all the effort that's gone into building quantum computers is the rise of quantum circuits in superconducting quantum circuits. But we'll possibly hear more about that, John, I think, will we? Okay, good. So I won't say more about that. This is the one I'm particularly excited about. This is doing it again with photons. So I'm back to where I was at the beginning, photons on beam splitters. We now know we can build very complex integrated photonic circuits and do very complicated interferometers to process information with information stored either as the direction of a given photon, that is which waveguide is it in, or its polarization. One really nice experiment that we ran recently to show how these things could be more efficient than classical machines was based on this idea of Aronson and Arkhipov, who pointed out that what Shaw's algorithm really says is that predicting the probabilistic results of a given quantum mechanical experiment to finite accuracy cannot be done by a classical computer in probabilistic polynomial time. That is, it can't be done at any reasonable time. But who cares? We're not going to predict it. We're going to build the machine and run it and just sample the probabilities just like we did for the gravitational wave detector. And that's what my colleague Andrew White did. We noticed many years ago, but didn't appreciate the computational significance of it, that finding the permanent of an n by n matrix is hard. So, I don't know, do people know what a permanent is? Everybody knows what a determinant is. Well, a permanent is where you forgot to put the minus signs in, which students sometimes do. Not because they're trying to find a hard problem, but because they're actually trying to solve an easy problem and got it wrong. So here's the permanent of this matrix. You can easily see that this would be a minus and this would be a minus if this was a determinant. Permanents turn out to be intimately related to expansions of very large polynomial functions, and finding them is a particular kind of hard problem in the language of computer science, sharp P, in fact, complete. So Arkhipov and Aronson realized that you could do this with single photons on beam splitters and moving mirrors and all the rest of it very, very efficiently. It turns out that if I have lots and lots and lots of photons going in fact, but I arrange it so there are more possible beam splitters than there are photons. They might have 10 photons and 20 beam splitters. They have more and more beam splitters in here. Then they're not all equal, not all 50-50. And some of the mirrors are moved a little bit to get some phasers in. Then I ask, what's the probability that I get 1 photon there, 2 there, and 3 there, and so on? So I want to predict the probabilities for detecting photons. Turns out that probability is determined by a permanent, which is hard to calculate. So if I put, 500 beam splitters in here, that's really hard work trying to predict what's going to happen there. Better just to go and build it. Doesn't involve anything complicated, just beam splitters and phase shifters. That's not too bad. Building lots of them and getting them to all sort of work properly is a non-trivial matter, but they managed to do it for about 5 or 6. And they built this photonic boson sampling circuit, which was published earlier this year in Science. So the distribution of outcomes just evaluates the permanence. So you need to run it a few times, but as in all probability statistical measurements, you need to run it a few times, but you can get the permanence. So let me now conclude by saying a few things about engineered quantum systems. So I pointed out that at the very beginning, we're now at the phase where we have enough control over individual bits of stuff to start putting individual bits of stuff together and trying to get control over it at a higher level. Here's a nice example, and John Martinez will talk about some of these this afternoon. This is from John Teufel's group down in NIST. Basically, it's an LC oscillator. There's a capacitor and a big spiral, which is the inductor. But one of the plates of these capacitors is suspended 50 nanometers above the lower plate, so it can vibrate up and down. Furthermore, the whole thing is a superconducting device, so that it essentially operates in this deep quantum regime if it's cold enough. That is, there's no dissipation, no randomness coming in from thermal effects. Even better, they can cool it to such an extent that the vibrational motion of the upper plate is fully quantum mechanical. So we have here a device which is definitely not a single atom. It's not even a molecule. You can take it out of the fridge and look at it. It's not that big, 20 microns, but you can see it. And it's completely classical. It doesn't do anything exciting if you don't cool it down. As soon as you put it into the dilution fridge, you discover that when you fiddle the voltages going in and look at the voltages coming out, there's something weird going on in between. And what's going on in between is the fact that it's a quantum system. But this one you've engineered to your purpose. It has a superconducting quantum circuit and a vibrating capacitor plate. We don't describe this in terms of the individual atoms and electrons that make it up. We back right off to a higher level, describing it directly in terms of the quantum circuit. This is really easy. You could teach your students to do this. You just write down the circuit equations, Kirchhoff's rules. And then you just impose commutation relations on, say, the charge on a capacitor and the flux through an inductor, and you're done. Of course, getting stuff to behave like that's a non-trivial matter, and it's taken a little while. So the key point of an engineered quantum system is they're fabricated artificial devices that operate by the control of quantum coherence in a highly macroscopic way. They involve many, many atomic systems, and typically one is quantizing a collective degree of freedom like a current or the bulk elastic vibrations of an entire capacitor plate. Here's another kind, these optomechanical systems, where we get control over the coupling between the light in some vibrating waveguide. So this is the one we're particularly interested in. It's a little piece of silica that's been melted and sort of reflowed to form this circular waveguide for light, like an optical fiber donut. The light runs around in here as a whispering gallery mode, but as this entire platform flexes, the path length for the light changes, and we start getting a coupling between the light and the motion of the device. So these devices are now being built in many labs around the world, and again, they're an example of an engineered quantum system. So now you begin to see that the old picture we had, that people used to say, oh, well, quantum mechanics is weird, but that's okay. It's weird for atoms, and we're not atoms, so we don't have to worry about it too much. This is no longer the case. The divide between quantum and classical is no longer that between atomic and macroscopic, not between microscopic and macroscopic. The border is moving. As we get control over increasingly many more degrees of freedom, it's just a question of money and engineering capability. Well, it's easy for a theoretician to say that, but at the end of the day, it really is just a question of money and experimental capability. So we've already seen that we can move from LIGO, these kilometer-sized devices, right down to these nanometer-sized devices and do quantum mechanics all the way. So sooner or later, some of these issues that we know lurk in the background, our confusion about measurement and all the rest of it, are going to be manifest right there in the lab. We'll probably be able to build some of these devices and package them up for high school experiments at the end of the day. This is one we're particularly interested in. So as I said, as it vibrates, the light rattling around in here gets a phase shift. These things can be used for ultra-precise sensing. One of the ones we're particularly interested in is putting some magnetorestrictive material on top, so in weak magnetic fields it strains the device a little bit, and you pick that up in the optical signal. Large arrays of those can be used to build very, very weak magnetic field sensors that operate at room temperature, which would already, in the lab, we see they have sensitivities as good as the best SQUID, low temperature magnetometer devices that people use in biomedical applications. It'd be great if these things could be solved there. So the quantum world is strange. We accept that. That's fine, but let's move on. So the whole idea of engineered quantum systems is making this strangeness useful and getting, this is the way the world is built, right? It's just the way it is. And we begin to understand the rules enough that we can begin to order that world to our purpose and start engineering new technologies. There are going to be some big surprises in store. There's no doubt about that. I'm just taking it as axiomatic that quantum mechanics keeps applying no matter how big the system is. That may not be true. It may turn out that we fail to build a quantum computer precisely because we test quantum physics to destruction in the effort to do so. That is, there's some scale at which the whole theory runs off the rails. There's still the nagging suspicion of gravity not fitting into the picture. Some of you may have heard previous talks here on this. We really don't have a good idea yet of how to quantize gravity. There's some good candidates, of course, in string theory and loop quantum gravity. But not enough data yet, in fact, very little data, probably no data, to pin down what exactly a quantum theory of gravity might be. But our efforts to build larger and larger mechanical systems of bigger and bigger mass will eventually have to deal with gravitational interactions between the bits, and we'll be forced to face the issue. So while it may be strange, it enables powerful new technologies. And so we can take Schrödinger's vision, which was created in the attempt to explain measurements made upon atoms, to start to engineer an entirely new kind of quantum technology. So strange but true is the lesson, but even better, useful. So thanks very much.
So thank you very much, Jerry, for this beautiful lecture. Now we are open to questions now, and let me just remind you that you should wait for the microphone before asking your question.
Okay, thank you. Your talk is giving me a different perspective, but usually when we hear about quantum entanglement or coherence, you hear particles interact and entangle. My question is, if particles before detection have infinite presence everywhere throughout space, why aren't they all entangled? What determines the radius of interaction and why?
Okay, well that's a very deep question. As I said, entanglement is how we describe correlations we see when we make joint measurements on some compound system. Whether we explain that in terms of entanglement, of course, is predicated on that's the kind of measurement we're going to make. So we already make some split of the system into parts. And that's us. We're doing that. So in the classic example of producing photon pairs, the light interacts with the crystal in a complicated way and produces these photon pairs. The reason we see the correlations is we choose to put one detector over there and one detector over there. They're localized in space, so we now can think about correlations between those two detectors, and we explain those correlations in terms of the entanglement of these two photons. Now, let's suppose I made a different choice. Let's suppose I didn't decide to put the detectors out there. Let's suppose I just decided to detect whether or not there were 0 or 2 photons. That's a single event. So I'll always get 2. I won't get 0, and I won't get 3 or 4. There we wouldn't describe the state in terms of entanglement. We'd just describe it in terms of the probability amplitudes we need to get a total photon number. So it's always the case in any quantum entanglement experiment, you first make a decision of how you're going to partition the system, and that determines whether or not you think of it as entangled. Now this can get pretty weird. So in the ion trap case, for example, what's typically done, let's suppose we have 2 ions in the trap, and we cool them right down to the ground state. In fact, there are 2 possible modes of vibration. They could be doing this in the trap, or they could be doing this in the trap. So what's done is both of those vibrations are cooled to the ground state. So it's just sitting there sort of fluctuating a little bit in the center of mass mode and in this breathing mode. So that refers to the collective motion. And that's not entangled. They're both in the ground state. Nothing more to be said. However, if we go in and look at the measurements of the position of each one separately, so we now decide to partition them and look at the displacement of each one separately, they are entangled. So in the case of measuring the collective motion of the two ions, the state we would choose to describe the measurements is not entangled. If we do measurements on each ion separately, we see funny correlations, and we say the state is entangled. So in some sense, entanglement's in the eye of the beholder as well as in the quantum system. In fact, it's even worse than that. It turns out, based on that analogy I just gave, that in fact, if the electromagnetic field is in a vacuum state all over the universe, every single mode is in its ground state. That's not entangled. But locally, if I started doing electric field measurements locally, it would be entangled. So even a universe filled with nothing would be entangled if you looked at it in the right way. So it's a strange feature, which comes back to the motivation for your question.
Okay. I have a question whether you think there's a significant probability in the next few decades of creating actual devices, machines, where I have something practical in my pocket and I push a button and I walk through a wall, or I teleport my information to Australia,
I thought you
something.
said practical. Okay. It will definitely be the case that quantum-enabled and quantum-enhanced technologies will enter the marketplace soon. I've already hinted at one, these weak magnetic field sensors, incredibly sensitive accelerometers. So these are devices that are pushing down to the lowest possible accuracy you can do measurements in a quantum world, and then working with the Heisenberg uncertainty principle to do a little bit better. So they're happening now, and they will come. Quantum computing is, of course, the big one. Maybe a few decades to some interesting special purpose machines. Is again a question of money and effort. Now, teleportation, okay, I think that one's going to be a little way off. Which, well, you mentioned Brisbane, yes. It's basically you just head out that way and keep going for a while. It's just on the other side of the pond. But it does take a while. It'd be fantastic to just teleport there and back. But I'd be a bit worried about doing that in a quantum world, to be honest.
Yes, with your ion traps, I wonder if you don't go to the ground state, but say you go to some state slightly above, and characterize what's called a negative temperature. Would those, particular states be correlated? Would they be, how would you characterize a negative temperature in the context of this talk?
Okay. So temperature typically refers to a thermodynamic system which is in equilibrium with some environment. And we know, let's just take a two-level atom. So if a two-level atom is in thermodynamic equilibrium with its environment, an ensemble is the sort of fixed probability of finding one in the ground state and fixed probability of finding one in the excited state. And the probability in the ground state is bigger than the excited state. As the temperature goes up, the probabilities become equal. Okay. Now let's look at one atom. So we go and look at one of the atoms that's in thermodynamic equilibrium. We don't find it jumps between the ground state and the excited state all the time. And the transition rates are equal. That's determined by something called detail balance, which underlies thermodynamic equilibrium. So if you do those measurements and sample it, you would assign a temperature because you would back out eventually that it was in thermodynamic equilibrium. You're more likely to find it in the ground state than the excited state. If, however, you set it up in such a way that you found it more likely to find it in the excited state and the ground state, and you pretended that it was somehow or other interacting with a heat bath, you would assign a negative temperature to it to describe that unusual imbalance. People do that. So negative temperature often refers to systems that are not in thermodynamic equilibrium, but are nonetheless randomized in some way, and it's a convenient way to describe those systems. Biased tunnel junctions in electronics are similar because the bias creates a potential difference across the junction, and the Fermi level on one side is higher than the Fermi level on the other, and you can think of that as a negative temperature as well. But it's out of equilibrium because of the bias. I don't know if that comes some way to answering your question.
So I'm new to all this ideas here, but I was just wondering, what is the factor in terms of improving computing power if we're able to create a quantum computer compared to what we have now?
So the difficulty in creating a quantum computer is making sure you have control over quantum coherence, which means you have to make sure that you don't lose track of any of the probability amplitudes. So let's go back to the case of a single qubit, the photon going through the two beam splitters. It's either up or down. We only need a list of two elements, which are the probability amplitudes. So long as if I'm going through sufficiently many bits, so long as I always keep track of those two amplitudes, each of which is a complex number. So there are 4 in principle, but the probabilities have to sum to 1, so that gets rid of 1. So there are 3 numbers in principle you need to keep track of. Now, if I may begin to lose track of some of the numbers, but keep track of the overall amplitudes, the magnitude squared. So I've got track of the probabilities, but I've lost track of the detailed pluses and minus signs. That would be called decoherence. That would be called losing ability to track coherence. Now, how that would happen is if there was some beam splitter or some mirror that was moving in a way that you didn't know about. So it was introducing an extra little rotation or an extra little phase on one of these probability amplitudes. So that would lead you to lose track of the probability amplitudes. So at the end of the day, it just got scrambled. You couldn't have this clever arrangement of processing amplitudes, 2 to the n amplitudes, 2 to the n binary strings as amplitudes all the way through to the end if you started losing track of all these amplitudes. Now, in the case of 2 to the n amplitudes, that you can imagine is a pretty big task if n is, 1 million. So this is why it's hard to build a machine where every single bit of the machine, you know exactly how it's controlling the probability amplitudes. One way to fix it is to cool everything down. That's a good start, but you still need much more. Now, eventually, you will never be able to get rid of all the sources of noise and uncertainty. But fortunately, we have something called quantum error correction, which is the true miracle of quantum mechanics, frankly, from my point of view. Quantum computing, as Deutsch came up with it, would have remained a sort of obscurity for theoreticians, was it not for quantum error correction. It's the fact that quantum coherence itself can be used to fight the errors. So the idea is to encode your information in such large coherent structures that small errors can still be detected without losing the information. So the central difficulty is in building a quantum computer modulo quantum error correction is getting sufficient control over all these probability amplitudes at each step in the machine. And we are still developing the tools to do that. We're still developing the basic quantum technologies that we need to build this ultimate quantum technology, a quantum computer.
Hello. What factors will constrain the speed and the memory of a quantum computer? Is there any limit to what we can achieve? And if yes, what constrains those limits?
That's a good question. Okay, so the speed, okay, so this is also connected to this question of keeping track of all the probability amplitudes. So if you can do things quickly before some disturbance comes along, that's good. So faster the better, basically. However, it can't be too fast, otherwise you begin to lose control of the quantum systems as well. So what can happen, for example, if you have a 2-level system and you're trying to very quickly change its state, the technical word is you eventually get to the point where you see it's really not a 2-level system after all. There are other levels in the atom somewhere or other that information begins to leak off in. So there are often fundamental physical reasons that prevent you from going arbitrarily fast. So the speed will be determined by the fundamental physics of the device that's being used to implement the calculation, and the fact that it has to satisfy fundamental quantum rules. Now, for memory, do you mean the size of the memory?
Yeah. How much information you can store?
Okay. So again, the question is storing it reliably. So you can store a lot of information, 2 to the n in just n registers, but you've got to make sure it's still there when you come back to address it. And if you lose track of the probability amplitudes involved, then you're in trouble. So this is like a quantum computation where you just do the identity algorithm, right? You just store the stuff, wait, hope nothing happens, and then come back and see if it's exactly what you thought. So what will limit the size of memories is, again, this question of control, keeping track of coherent control for long enough.
So it looks like the lifetime of the levels will dictate the speed of the...
That's it.
Thank you.
So you've addressed speed and you've addressed accuracy in dealing with computing. The supercomputers take a massive amount of power. So if you have a supercomputer that processes at a rate, and you take a quantum computer to process at the same rate, you're definitely going to be processing it faster. But as you said, you're talking about supercooling and things like that. How about power consumption?
Now that's a really good question. Now it turns out all our supercomputers are built out of devices that necessarily erase information. They don't have to be, but let me tell you why. Let's suppose you take an AND gate where there's two binary inputs, so there are 4 possible inputs. There's only 2 outputs, 1 or 0. So clearly it's erasing information. There are 4 distinguishable states that go in and only 2 distinguishable states that come out. It erases information. Now there's a fundamental connection between erasing information and thermodynamics that was discovered by, well, probably many people, but most clearly stated by an IBM physicist, Rolf Landau, back in the late 60s, early 70s, that said the minimum you need to dissipate in energy to erase 1 bit of information is basically kT, Boltzmann's constant, times the temperature of the environment into which the information is lost. So all our big machines dissipate vastly more energy than that, because they're all based on dissipative elements. They basically use switches that get locked on particular states by dissipation. So they raise information, there's a heat cost, therefore they're fundamentally irreversible. If I give you the output for an AND gate, you can't tell me, well, you can tell me at least one case it isn't. If I tell you the outcome is 1, you know it wasn't 0, 0, 0, 1, or 1, 0. So they're not logically reversible, and they're not physically reversible either. So they're not time reversal invariant, so they're definitely not quantum computers. So the nice thing about a quantum computer, and this is partly where the whole business started, is that if we're going to do everything in this quantum way, it's necessarily reversible and necessarily does not dissipate any energy. Except for the business of error correction. Error correction has to dissipate energy because you've basically got to dump entropy somewhere. The errors are trying to randomize your machine and you're trying to suck it out and dump it somewhere. So there will be energy constraints on a quantum computer, but in principle they should be able to operate at vastly lower powers. John Martinez may have something to say about this at some point. At the end of the day, there's energy got to go in one end and you've got to have enough signal to measure it at the other end. So there is still some power requirements. But because they're not dissipative logic machines, in principle, they won't necessarily be subject to the same constraints as classical computing engines.
Does entanglement, would that allow us to create a device that has instantaneous communication across long distances?
In a short answer, no. So to see the entanglement, you have to see the correlation, which means that, you know, if I'm in Australia making my measurements on one half of the system and you're here making measurements on the other half, we're just getting random numbers. We only see the correlations when we put the tables together and start looking at each run. Just like in the case of Bellsville and the twins. Whether I get plus or minus for any given twin is completely random. I only see the correlation when I know the result for the measurement on the other twin. So anything that you can do based on correlations requires you to bring information back to the same place. And that takes time. In fact, it can't be done faster than the speed of light, so there's nothing superluminal about that.
Hi, Gerald. Great talk, by the way. I really enjoyed it. We have in residence right now at the KITP a journalist who wrote a book about the many worlds interpretation, and its creator, Hugh Everett. And I noticed you mentioned Deutsch, who famously or infamously invokes the many world, and even says that he might be able to come up with a way to verify this. It's not just an interpretation in his opinion. In fact, it's something that could be tested. I wondered if you had an opinion about this point of view. Yes,
I have an opinion, so I stress this is an opinion. These are based in interpretations of the formalism of quantum mechanics. So the idea is we have the mathematics, we crank the handles, we can do the experiments, and everything matches up nicely. We have a box, we send in classical control signals, classical measurement results coming out. We correlate the two and we see we need the quantum theory to explain what's going on. Okay, we all agree on that. The question is, what story do you string around what's in the box? So we're always trying to make little sort of stories to explain what's going on, often involving causality and so on. So Deutsch's picture for why this machine works the way it does is, you know, there are these 2 to the n possibilities that when you look at it, you see one of them. but they all run together. His idea is that they're actually all running in multiple worlds, multiple universes. Okay, so that's fine. It's a consistent interpretation. It's not the only one. It doesn't change how you do the experiment in any way, and it doesn't change the results. So it really is an interpretation. My personal opinion is it seems a little extravagant. For example, these sorts of gates that we build with photons, I didn't tell you about one particular kind of experiment where if you fire 2 photons simultaneously at a beam splitter, then you might think that there are 4 possible outcomes. 2, 0, 0, 2, 1, 1. Turns out you never see 1, 1. The probability amplitudes cancel completely, and you never see them. So now you might say there's some sort of weird interference going on out there in the multiple universe, but you don't have to say that. It's purely an interpretation. Now it may be useful for theoreticians to use that interpretation to dream up modifications to quantum mechanics, which we can go and test, but nobody's done that yet.
I have a question that will take things in a little bit different direction. As a high school physics teacher, I'm wondering if you can give me any advice as to what I ought to be telling my students. Some of my goals along the lines of quantum mechanics are to be telling them about Bohr's model, about quantum leaps, about the fact that, at least in my view, these are things that happen in the very small world, not so much in the macroscopic world, although you're making me think a little bit differently about that today. About Heisenberg's uncertainty principle, Schrodinger's cat, things along those natures, the particle nature of light. Can you give me anything else that I ought to be having them learn as they do my classroom?
That's all great. Keep telling them that, but tie it to the experiments that show us that's what happens. So quantum jumps is a good example. It's been around since the beginning of quantum mechanics. Schrödinger, curiously enough, didn't like it very much. He was a little bit confused about this himself. In a letter to Eddington in around 1950, I can't remember the exact quote, but he says something like, well, all this quantum jumping really is due to the fact we never really deal with one quantum system. We're always dealing with an ensemble, and the statistics we see is really just the statistics of the ensemble. Okay, that was fine back in 1940, 1950. It's not fine today, because we can do an experiment on a single trapped ion. We can sit there and look at it over and over again, and you can set it up in such a way that you see the quantum jumps. You see it blinking on and off, purely in accordance with the rules of quantum physics. So there you can do a measurement on a single quantum system over and again, you can see the jumps. So when you talk about quantum jumps, perhaps show them those beautiful experiments from Wineland's lab in Boulder. In fact, Dave Wineland and Serge Hirosh got the Nobel Prize in the last award round for beautiful experiments on single quantum systems showing these lovely features. They've also done experiments where they make a kind of Schrödinger cat. Superposition, for example, they managed to create a state where an ion, single ion in a trap, was simultaneously, as we would say, a quantum superposition of being on the left of the trap and the right of the trap. It's only one ion, right? So you can't say it's simultaneously in both places. That would be a bit crazy, because when you look, you don't see it in both places. You see it in one or the other. But it's in this quantum superposition. So again, when you talk about cats and superpositions, try and find some nice modern experiment where that's what people see. Does that help?
Yeah, I've got some research to do.
Okay. Actually, maybe somebody should think about a book along those lines. That wouldn't be a bad idea. Yeah. Somebody, not me, but...
And Gerard, just a question on this quantum jump thing, because Schrödinger didn't like it, and in fact now we have experiments showing that. But people sometimes ask, is that instantaneous? Is something that happens, with delta t equal to 0? In fact, even Hirosh's experiment, it takes some time to measure that. So could you comment on that?
Well, that's true. Well, now we have to dig down and look at the actual experiment. So to see a quantum jump, you have to first go looking for quantum jumps in the first place. So what you're trying to do is make a measurement that says which state is the atom in. So it's being illuminated by light. The light's driving some transition between two states. Now I need some other way to go in and have a look to see which state it's in. So I need to bring in some other field which interacts with the system with its associated timescales. Then I need to do the optics to get the signal out. If it's to my eye, there's some timescale associated with the response in the eye. If it's just a predator detector in a computer storing the results, there's another timescale. So in the physical sense, there are all timescales associated with these things. So how fast does a jump take? Well, as fast as it takes to say it, is my guess. When you see it jump, then you know it jumps. So this comes back to the distinguishing between measurements on ensemble and measurements of a single system, conditional states versus unconditional states. But to do the experiment, to see the jumps, you need a particular physical situation with associated timescales. Now, you don't have to look for jumps. You could do something completely different. I could just say, let's look at the electric field being radiated by this atom. So then I need to set up a different kind of experiment. I need to set up some sort of interference experiment to take the field that's radiated and mix it with another field. Now I don't see jumps at all. Same atom, same physical situation, just look at it differently. Now I see a smoothly fluctuating electric field. Well, not that smooth, but sort of very noisy electric field. So to see quantum jumps, you have to look for quantum jumps. To see quantum noise in this diffusive way, you have to look for quantum noise. So as Bohr said, it's the context of the experiment that is important. I think that's a hint to stop talking.
I think break time. Okay.